My name is Andy Pavlo. I am an assistant professor at Carnegie Mellon University. So today I'm going to talk about research we've been doing at CMU on building autonomous database systems. So today's talk is going to be focused on how do you actually want to design your software to actually make it autonomous. And by autonomous, I mean a system that's able to deploy, tune, and configure itself automatically, all without any human intervention. So I'll say up front that this is a lofty research goal. This is going to take probably 10 years to actually come to fruition. But this is what I'm spending all my time on, my students' time on on campus. And I'll say also too that there's whole other talk I could give about the machine learning algorithms you need to have an autonomous database system. But that's not going to be this talk. This talk is really focused on the engineering side of things. Are we good? OK, sorry. All right. So before we get started, the overall layout of the talk is, first I'll talk about the background of what I mean by autonomous system and what kind of work has been done in this area for the last 40 years. And then again, we'll talk about the design principles you need to have in order to build a database system to be autonomous. And then what kind of database talk would I give if we didn't finish up with a rant about something about Oracle, right? So we'll finish off with talking about Oracle's self-driving database system that they've announced in the last 2 years. So by all means, ask questions as we go along, and I can repeat them back. So the reason why we're interested in building autonomous systems is sort of obvious, right? Database systems or managing database systems are a very expensive and very labor-intensive process. The average salary of a DBA in the United States is roughly about $89,000 a year. And so again, we're in Russia, so we can translate that to rubles, so it's 5.9 million rubles a year. So this is really expensive, right? You're paying humans to basically babysit your software. And about the total cost of ownership of a database system, about 50% of it will be spent on, on these DBAs, on the personnel. And so when you start looking at really, really large deployments, right, tens of thousands of database instances, the complexity of these environments has surpassed what humans can actually reason about. And everyone's sort of punting on this problem now and just sort of configuring things to be with the lowest common denominator of trying to get the best performance. And there's a lot of money that's being left on the table if you could actually tune these systems on a per application basis or per environment basis and get the best performance. So this idea of autonomous, again, database systems is not new. The story of them actually really goes back all the way into the 1970s when people first started looking at, first started building the original database, or relational database systems. So back in the 1970s, these were called self-adaptive databases. And the problems they were trying to solve are sort of the classic database design problems that humans still struggle with today: index selection, partitioning and sharding, and data placement. And so what people developed back then were these tools that would assist human DBAs with deploying their database systems. And so these tools essentially work the same way that the modern variants work today, right? You have some human DBA, they prepare a workload trace of the queries that the application is executing. And then they feed this trace into a tuning algorithm that then builds an internal model about what it thinks how the application is using the database. So if you were building a tool to help you automatically select indexes, you would build some internal histograms and say, here's how often each column is being accessed. And then you feed this information into a search algorithm that's going to look over a bunch of different combinations. So again, if we're trying to pick indexes, it's going to look at different columns you could index in your database. And it's going to use an internal cost model to say, this one index is actually going to provide the best performance over the other indexes. And then it makes a suggestion to the human about that index, about that change it could apply. And now it's up for the human, again, to look at that suggestion and not only decide whether it was the right thing to do, but also has to decide when's the right time to actually make that deployment, apply that suggestion. Right, so they have to sort of know how the application is being used, what's the downtime for your users. Like Sunday at 3 a.m. is when your demand is low in the database, so that's when you can rebuild your indexes. So as I said, all of the design tools back then sort of essentially work the same way. And just to give you an idea of how old this problem actually is, one of my advisor wrote a paper on this in 1976 on automatic index selection, and he's dead, right? So people have been worried about this for the longest time, and things haven't really got that much better. So then now we entered into the 1990s, And people were essentially working on the same kind of problem, which is instead of calling them self-adaptive databases, they were called self-tuning databases. Right? So again, the classic problems were index selection, partitioning, and data placement. So the algorithms got slightly better, the tools got slightly better, but at a high level, they essentially work the same way. And the one group that was actually the vanguard of the self-tuning movement was actually Microsoft Research with their Auto Admin project. Right? These are really great tools that they developed in the late 1990s, early 2000s on, again, providing these suggestions to humans about how to tune their database to work better. And the key idea that Microsoft came out with that was different than what was done in the past is, rather than having the tuning tools maintain their own cost models about what they think is a good design choice, they actually just reuse the database system's query optimizer's cost model to help it figure out, whether one index was better than another. Right? And this sort of makes sense when you think about it. Right? You want to know whether one index is going to help improve your queries. Well, it doesn't matter how great the index it is if the optimizer doesn't pick it. So you use the optimizer to figure out whether it's actually would pick something. So there's a paper from 2007 from Microsoft Research that lays out, it's a retrospective of 10 years worth of research in this area. And it does a really good job of talking about the hard problems every step along the way. Now, the other thing that people looked at during this era of self-tuning databases was how to do automatic knob configuration. So a database knob, or it would be some kind of configuration parameter you could set to modify the runtime behavior of the database system. So the one that almost every single database system has is the buffer pool size. Or you can have other knobs that control things like lock policies, how often days flush out the disk, things like that. And so the reason why people are looking at how to automatically tune the knobs of these database systems is that the complexity of them has grown greatly over the years. So to give you an idea how bad things have actually gotten, this is a survey my student did looking at the last 15 years of all the releases for Postgres and MySQL. And what they found is over a 15-year period, Postgres had 5x more knobs since the beginning, and MySQL added 7x more. Now, not all of these knobs actually control the runtime behavior. Some of these things are for like file paths or network addresses where only human can actually ever set them. But there's certainly, we see maybe several dozen, up to maybe 50 or so for each of these systems, knobs that actually can help, can affect the runtime performance for different applications. So again, this has gone past what any human can actually reason about. So then we enter the era of the 2010s, sort of currently where we're at now. And this is what I call the era of cloud databases or cloud managed databases. So there was a lot of work on automating the deployment of a large number of databases in a cloud environment. So the big thing that the major cloud vendors are worried about here is how to do tenant placement or tenant migration. So how do you figure out how many resources each tenant is going to need, and then you try to assign them to the machines that are going to maximize performance or meet your SLAs with reducing the overall hardware cost for your system. So Amazon, Microsoft, and Google are all essentially doing this kind of work, but it's all underneath the covers at the operator level. Only until very recently are the cloud vendors actually now looking at how to tune the individual database systems themselves. Right? But all this work done before is all, again, you don't see this is all just them to make their bottom line be better. So given I spent the last 5 minutes talking about the last 40 years of database research on autonomous systems, why is this all insufficient? Right? Why can't we have a truly autonomous or self-driving system available today? Well, it's for 3 reasons. The first is that all of these tools, with exception for the cloud vendors doing tenant placement, these are all advisory tools, meaning they're making suggestions to a human, and a human has to make the final value judgment about whether that's the right thing to do. But it's more than just whether it's the right thing to do. They have to observe over time when they make the change if it continues to be the right thing to do, because the application can evolve, the needs can evolve. Right? And then they have to learn about what the change they applied and then feed that back into their own internal model of how they actually want to make decisions in the future. Right? And if you can do this for one database system, but if you want to scale up to tens of thousands, this is impossible. The next issue is that they're all reactionary measures. So in all the examples I showed, you take a workload trace of the history of things happened in the past, they had some problem, you feed that into the tool says, yes, I know how to fix that problem, right? And it's only fixing the problems that occurred in the past. It can't look ahead and say, well, what's coming down the pipeline that I need to worry about and prepare the system accordingly. Humans can do this now, right? They do this manually, but all these tools can't do this. And the last issue is that there's no transfer learning in any of these solutions. So what I mean by that, if I come along and I have a tool that can tune my one application, right, on this one database instance, now if I have another application on another database instance, there's nothing I've learned from the first session, the first application, that helps me tune the second one better. It's always like they're starting from a cold start. They have to bootstrap all the knowledge about what's going on, right? You think about humans don't work this way, right? If I know how to tune one application a certain way, I can see the same patterns in other applications and maybe tune them much more quickly. But none of these algorithms, none of these tools work this way so far. So why am I confident that things are so different now? Well, it's sort of the classic story about why big data or AI machine learning is hot now. We have better hardware, meaning we have better storage to store more data, and we have accelerated hardware to do better computations to train the models we need in our machine learning algorithms. We have better tools, software tools that are available to us. Right? In the old days, you had to be an expert in MATLAB or low-level linear algebra in order to write some machine learning algorithms. But now we have things like Torch and TensorFlow that make these things more accessible to systems programmers. And of course, we have a better appreciation for data, right? People recognize that this data can be used to help tuning decisions in the future, so people aren't throwing away as much data as they used to be. So the sort of goal of our research is that we seek to complete this circle in autonomous database systems, where we can make the same kind of suggestions that the previous tools could do, but rather than relying on a human to decide whether that's the right thing to do and when to actually deploy it, we'll do it automatically, and then have a feedback mechanism to learn from our decisions and see and get better over time. So I'm going to talk about 3 projects that we have ongoing at Carnegie Mellon University, and they're sort of looking at this problem in two different ways. So the first is looking at how can we tune databases, treating them as black boxes, right? How can we tune existing database systems where we don't control the internals of the system, we only see what the database system exposes to us. And the second project is to look at it. If you build a new database from scratch, from the ground up, knowing that you wanted it to operate autonomously, what kind of optimizations or what kind of things you could do that you may not be able to do otherwise in existing systems. So I'll go through each of these one by one. So the first project to tune existing systems is a project we've developed called Autotune. And you can think of this as like database tuning as a service. So the idea is that you come along with your database instance, you upload the runtime metrics of what your application is doing on that database system. We'll crunch on it, and we'll come back with a recommended knob configuration that we think will improve your objective function, right? Whether it's latency or throughput or whatever you want, we try to optimize that for you. And so the key thing that's different about Autotune, what's done before, is that we can actually reuse the data from previous tuning sessions to make new tuning sessions go better. So that means if you come along with your Postgres installation and it has an application we've never seen before, but it has certain characteristics, or using the database in a way that looks a lot like databases we've seen or applications we've seen last week. Since we know how to tune those from last week, we now know how to tune yours more efficiently. Right? So at a high level, it works like this. Right? You start with your target database, and this could be Postgres or MySQL or VectorWise. And you're going to install a controller in the same administrative domain that's going to have 2 purposes. So the first, you're going to have this thing called the collector that collects the current runtime configuration and the runtime metrics of your database as the application is running queries on it. And then we're going to upload this to our tuning service. Right? This is either running on-premise or in the cloud. It doesn't matter. And then we're going to store this in our own internal repository of all the tuning sessions we've seen before. So there's going to be 2 stages before we make recommendations based on the data we're collecting from the database. So the first is that we have to look at the runtime metrics and figure out actually what matters. All right, so this is an example of what you get from MySQL when you run show global stats for InnoDB. And so MySQL is going to spit out a lot of metrics, but not all of them are useful for us. And this is one of the big themes we're going to see as we go along. We talk about the machine learning side of things, is having a lot of data is actually not always a good thing, right? Because now you have to it takes more data to figure out what's the signal versus what's the noise. So there's a bunch of problems in this that we had to figure out how to prune out things that don't actually matter to us. So for example, here I'm highlighting 2 different metrics. One is called InnoDB buffer pool bytes data. One is called InnoDB buffer pool pages data. Same metric, just in different units of measurement, right? So we can run statistical analysis on them, see that they're highly correlated, and figure out that, oh, these things are actually redundant, and we can throw one of them away. And that reduces the dimensionality of our training problem for our machine learning algorithms, and then it allows us to converge to an answer more quickly. We can find better solutions, better recommendations for you. So the next thing we need to do is essentially the same kind of thing for the knobs. As I showed before, MySQL has 500 knobs, but not all of them actually matter, and not all of them matter to different applications in the same way. So we need to do some statistical analysis on them again to figure out which ones actually will affect the objective function that you're trying to optimize more. So in this case here, we find that InnoDB buffer pool size and flush method and log file size, these three knobs actually have the biggest impact on performance. They have the strongest influence on lowering the latency for a transactional workload or OLTP workload. We also can find other interesting aspects of knobs that actually don't matter automatically. So in this case here, there's a knob called time mutexes. If you go read the MySQL documentation for 5.7, it'll tell you that this thing is deprecated. But from a machine learning algorithms standpoint, it can't read the documentation, so it doesn't know. It just knows there's a knob here. You can tune this thing on and off, and it's going to take a long time for it to figure out this actually doesn't matter. So we can pre-compute this ahead of time and figure out this knob doesn't do anything, but then we essentially blacklist it and don't worry about whether we're setting it correctly or not. All right, so then we're now going to feed this into our configuration algorithm. So we use something called Gaussian process models, which is an older method, right? You've probably heard of deep learning, right? It's the sort of can do the same kind of things, but without having to do deep nets. And we implement this on GPFlow, which is a Gaussian process model library, actually out of Russia, built on top of TensorFlow. And then it's going to produce a recommendation that it thinks is going to improve your objective function. And then we feed that back to an installation agent running inside the controller, which then will apply the change, flush it. You have to restart the database, unfortunately, and then repeat the process over again. So we'll go and collect some more runtime metrics, feed that back into our algorithms, see how we improve, whether we're getting better performance, make recommendations, and do this over and over again. So the key thing about Autotune that's different than some of the other tools that we'll talk about later on is that the only thing that the algorithms actually need to see are benign information about the runtime metrics. So we don't need to see your data, and we don't need to see your user queries, right? We just need to see pages read, pages written, right? And you have to make a hard argument that this is somehow proprietary to your customers or to your company, that you don't want to expose this out to the outside world. Right, so we don't need to see any queries. We can just do this based on the runtime metrics because we're making recommendations on knobs, not doing physical design here. So I'm going to give a live demo of Autotune, which is always dangerous, but so far I'm like 12 for 12. So there's a website we have set up here. I need a terminal. That's why I'm going to do it from my laptop here. And this is on Windows, so I don't have one. So these are going to be running machines back in the US at Carnegie Mellon. And we're going to run Postgres, and we're going to run Postgres 9.6, and we're going to be running the TPCC workload. And what we're going to start off with is a initial configuration you get when you install Postgres on Ubuntu. And I realize this is kind of lame, but I'll zoom in as much as possible, right? I'm running this now in a script. What's going to happen is we're going to start Postgres. We're going to use the initial configuration you get from Ubuntu. Thank you for taking the picture. And we're going to first run TPCC for 5 minutes, collect the runtime metrics, upload that to the Autotune service, and then it's going to crunch on it, spit back a recommendation that it thinks is going to improve your latency or throughput, apply the change, and then repeat the process. And it's going to do this while I give the talk, okay? And then we'll come back here and check the website, and we'll refresh it, and it'll have the data. So the database system is running on one machine, and then the service with TensorFlow is running on another machine, and it'll upload to this. All right, so we have some previous results I can share, though, from a paper we published in Sigma last year. So this is running Autotune, tuning MySQL and Postgres for TPCC, and our objective function is to improve throughput here. So we're going to compare the default configuration for both these systems that you get when you first install it with Ubuntu. And then we're going to run some open source tuning scripts that are available from Percona and some other Postgres consulting firm. And these are just using heuristics that say, for your hardware, you should tune your buffer pool size to be this size and other things. Then we have the configuration you get from Amazon on RDS when you deploy RDS for the first time. And Amazon's already tuned this for the hardware that you're running on. Then we have very expensive human DBAs tuning this. Again, we give them 20 minutes of time, and they can tune it any way they want. And then Autotune is doing what I'm showing in my demo. We're going to collect some data, upload to the service, crunch on it, and then keep making recommendations get better and better. So in the case of MySQL, we see that, again, the default configuration is always bad. The scripts do a little bit better. RDS does a little better. But the DBA actually does the best here. And so this is actually the top MySQL DBA at Facebook. He's also the top Lithuanian MySQL expert. The reason why Autotune is actually losing to the DBA here is because there's some knob that he's allowed to tune at Facebook that basically turns off fsync for log flushes, right? Because Facebook is OK with this. But that's actually something that we blacklisted in Autotune because the algorithms don't know whether you're OK with losing the last 5 milliseconds of data, right? Because that's a human value judgment. Facebook's OK with it. We don't know this. So if we go tune the same knob that he tuned, then we match up with what they can get. Right? But this is a good example of how we try to be conservative because we just don't know. There's certain aspects of databases that we don't know what the right decision is. A human has to decide. In the case of Postgres, we see the tuning scripts actually do quite well. RDS does a little bit worse. But we actually Autotune actually surpasses what the human DBA can do. So this is the top Postgres expert for the Wisconsin court system. You may have seen some of the work on serializable snapshot isolation from a few years ago. So it's from the same group there. So again, what Autotune is able to do here is we're able to find a sweet spot between the log file size and the buffer pool size that sort of balances the amount of memory that's being used from these two components and gets the best performance. So the main takeaway here is that Autotune is using algorithms, he's using machine learning, and we're able to achieve either the same or better performance than what very, very expensive human DBAs can actually do. And this is just for one database instance. We can scale out to tens of thousands of instances because it's just software. It's just data. So the next project I want to talk about is Peloton. So Peloton is a brand new database system we're building from scratch at Carnegie Mellon. And we're calling this the self-driving database system. The idea is that we want to see, well, if you control the entire software stack, what things can you do better than Autotune because you know exactly what's going on. You know what the full pipeline is or the full stack. So the way this is basically going to work is that we have integrated machine learning components or reinforcement learning components inside the database system, can observe all aspects of its runtime behavior, and then make recommendations. And we're going beyond just knob configuration recommendations like in Autotune. We want to do all the classic things that I talked about before, picking indexes, picking partitioning schemes, scaling up, scaling out, all those things. So the current name of the system is Peloton, but I will fully admit that we are in the process of renaming it. So in Russia, I don't know if you guys have the same thing we have in the US. I realize that the Peloton means fearless in Finnish. It also means platoon in French. But in the US, there's a bike company called Peloton that has a lot of money. Every time that they put out a new store or they have a commercial on TV, all my friends are always emailing me and saying, hey, look, they stole your idea, stole your name. Their commercials have really good-looking people running on their bikes, right? I can't compete with that. The other thing that also happened too was last week, Uber came out and said they have a new resource scheduler called Peloton. So we can't call it this anymore. We don't know what we're going to call our new system, but we just can't. We're not called Peloton. But for this talk, it's Peloton. Okay. What's that? The bike people. Yeah. My Peloton used to be based on Postgres, but we threw all that out. But yeah, we can talk about that later. All right. So I was going to go at a high level with the intuition of how this is all going to work. So we have our target database, and again, this is our software. This is what we're running, and we're going to collect the same workload history that I showed before that the humans would collect. But the difference now is that we're going to generate forecast models that allow us to predict what the workload cycles are going to be in the future, what the workload demands are going to be in the future. And so this is sort of why we're calling this the self-driving database system, because this basic idea is the same way how a self-driving car works. Self-driving car looks ahead and says, here's what's coming ahead of me in the road, and it can make predictions of how to get there. So this is sort of the same thing you would need in a self-driving database system. You need to be able to look ahead and say, what's my workload going to look like 1 week from now or 1 hour from now? So then we feed this into our planning component, which runs on TensorFlow, which we're currently calling the brain. If you're familiar with the AlphaGo work out of London by Google, DeepMind project, right, at a high level, this also works the same way. You have a Monte Carlo search tree. You look for different actions to apply, and that you're going to think you meet your objective. So the way it's going to work is you have a bunch of actions, like drop index, add index, scale up, scale out, whatever you want. And then you generate a sequence of actions that will get you towards to maximizing your objective function. And then what happens is you end up throwing away all but the first one, apply the change, and then observe its effect, and then repeat the process over and over again. So again, not to push the self-driving car metaphor too much, but this is essentially how a self-driving car works. Right, this is called receding horizon planning. I look down the horizon in the road and say, all right, I need to get there. And then you plan the sequence of actions to get to that horizon. Speed up, slow down, turn left, turn right, things like that. And then you throw all those actions away but the first one, apply it, then repeat the process again. So a self-driving car is doing this 30 times a second. In a database, it's a little bit longer, but at a high level, essentially the idea is the same. So the reason why we decided to build our own database system from scratch, rather than building something on top of Postgres or MySQL, is that, I'll be honest, those systems are actually too slow for what we want to do. Right? The way I sort of think of this is Postgres is beautiful. I love it. I use it in my class. But it takes a long time to build indexes, right? Because things are coming from disk. So you can think of this as if you build a self-driving database system using Postgres, you essentially have a self-driving semi-truck, right? You can see the dog down the road and you can avoid it, but if a kid runs in front of you, you're going to hit it because it's not that nimble. So we decided to build a system from scratch so that we can apply these changes and learn as quickly as possible what the right configuration is. So I would say where we're at in the research is that we have solved the first problem. So we have a paper in Sigma this year that uses a combination of deep learning and sort of classic linear regression or kernel regression to automatically predict what the workload's going to be. The big problem we don't have a good answer to is this part over here, the action catalog. Right? The problem isn't how to pick the actions, right? Because the Microsoft guys already did that. But it's how do you actually determine whether one action is better than another in terms of what happens before you deploy it and after you deploy it. How do you reverse things? If the human says, hey, build this index, and it turns out to be a bad idea, how do you reverse them and tell them why you reversed it? So there's a whole bunch of these other issues in terms of how we interact with our own system and the outside world that we don't have answers to, and this is ongoing research. So a classic story is that I can't say who it is, but there's a well-known database company who had an automatic index selection tool. And the tool was having this problem because some customer kept undoing all the indexes that the tool was recommending and applying. And then this happened so many times that the tool essentially got stuck because it didn't know what else to do, because everything that they suggested, the humans say, no, don't do that, you're wrong. So then when the developers actually reached out to the customer and said, why are you undoing all the index recommenders, index suggestions? The answer the customer gave was they didn't like the name of the indexes, right? So people are stupid, but we have to deal with them. And that's the thing I don't have an answer to. All right, so let's go check on the demo. So hopefully it's still running. I'm not going to bring up my terminal, but so we go back here, refresh the page. Right, perfect, OK. So when we started off, I'll read out the number. We started off getting the default configuration for Postgres. You got 623 transactions a second. And then after one round of applying the change or making a recommendation and applying it, we got up to 2,300. So I will fully admit I have given this demo multiple times. And so there's already sort of a corpus of sample data I've already collected. And that's why it's converging to an answer, a good answer very quickly. Right, so what would happen is if I didn't have all this previously collected data, it would sort of be a stepping function up to get to this point. So we'll let this keep on running, and then we'll check on it at the end, okay? All right, so given now, again, I've sort of discussed at a high level 2 different approaches to doing autonomous database systems. Let's actually talk about now how do you want to design your database system to make it autonomous, right? So I'm going to focus on 3 topics. So how to do knob configuration, how to do internal metrics, and how to do action engineering. And a way to think about this, again, is that we want to have the database system expose the right information to the machine learning algorithms in order for it to make the best decisions. And we want to reduce the amount of useless data we pass along to it so that it can converge to answers more quickly. All right, so we've already talked about this a little bit before. Any knob that requires a human to make a value judgment needs to be marked as off limits to the autonomous components. And that's actually just, you want to flag in PG settings or whatever your config file is to say an algorithm cannot tune this. Right? For obvious things like file paths, you need these for the system to actually operate correctly. For things like durability, isolation levels, these are things that the human has to make the value judgment, the algorithms can't. The algorithm will find that, oh, if I turn off fsync on my log, I'm going to run really, really fast. And it will do that. But that may not be what you want. All right, and for the knobs that you do want them to configure, you need to expose some additional metadata about how the algorithms can change those knobs. So obvious things like min-max range or enums if it's a categorical variable. If you have a knob that if you want to be able to disable a feature, don't use -1 or 0 to say turn off a feature. Have a separate Boolean flag for that feature, because again, the algorithms will find that setting things to 0 makes things go faster. The one that's a bit more tricky is how to handle deltas, right? And what you essentially want is non-uniform deltas. So let's say you want to set some kind of buffer pool size in your system. And you can it's a 64-bit variable, so you can set it from 0 to 2 to 64. But not all of those individual values are meaningful or actually will provide some new information to the algorithms. So essentially what you want is for different ranges of values, you want to say, here's the delta you should use. So if you're on a small memory machine, you want to increment that knob maybe by 10 kilobytes. But if you're in a large memory machine, maybe you want to increment it by 10 gigabytes. Again, this is cutting down the solution space. This allows the algorithms to converge to an answer more quickly. Any knobs that are constrained by hardware resources should be flagged or tagged as so. Right? This is kind of tricky and more nuanced, but think about this is I don't want to set the total amount of memory my application's using or my database system's using to be more than the total amount of memory that's available to me. Now, what gets hard is sometimes you want to over-provision, like with CPU cores, and how the algorithm is actually going to handle that, we just don't know yet. But basically, again, you want to be able to provide metadata to say this knob relates to memory, this knob relates to disks, and so forth. Because then you can figure out, you can learn from that what are the proper ranges you should actually be in. Any knobs that are able to tune themselves, we think they actually should be removed. This is not so much an issue in the open source guys. We see this more in the commercial guys. Because what happens is now essentially you have another externality that you now have to model in your machine learning algorithms. Right? So we're already modeling one externality would be the workload. Right? We don't have control what queries show up, so we have to build models to predict what's coming along. But now if you have something like Oracle's automatic self-tuning memory knobs, then if these guys are flipping around doing whatever they want, and it's not responsive to how you think you're tuning things, then this is something that you again have to model. So again, we only see this in the commercial guys, but we think all of these things need to be turned off or removed if you want to be completely autonomous. Now in terms of metrics, we want to expose basically the hardware capabilities that are underlying in the database system. So this would be things like CPU, memory speeds, disk speeds, network speeds, and things like that. And the way I think this should actually work is that you could sort of think of, you have like an internal catalog and information schema that says, here's what my CPU looks like. And because the reason why you want to do this is because if you're doing deployment on your Postgres or one machine or one database system on one particular hardware type, but now you run a more expensive hardware that has more resources, you may not want to tune those knobs in the same way. So if we expose this information to the algorithms, we can then use other machine learning methods to extrapolate what your hardware can do on this machine versus what it can do on another machine. All right, the next thing is that if you have any subcomponents that are tunable, then you need to make sure to expose all the correct metrics for those individual components. So to make this more clear, let me give an example of a bad system that does this, or doesn't do the right thing. And this can be my, RocksDB running as my rocks for MySQL. So RocksDB allows you to tune different column families, right? So you can have a multiple number of column families per table, and then for each column family, you can tune those things individually. So in order to figure out whether we're tuning these column families the right way, we want to look at the metrics and say, well, how is it actually using the hardware? So that's fine. You can go get this from the information schema for RocksDB. It'll give you a column family stat. But the problem is the thing that actually matters the most for determining the performance of the database system in relation to column families and how you can tune them is actually the number of reads and writes that it does. But MyRocks doesn't actually expose that anything in here on a per column family basis. The only way you can get that information is if you go look at the global column family statistics, right? So RocksDB bytes read, bytes written, right? So this is essentially somewhat useless to us because now these are aggregated, and if we tune an individual column family, we don't know how that affected the reads and writes that column family was doing. We'd have to collect a lot of data to then extract that out from the aggregated summation. All right, if you don't remember anything from this talk, the only thing you should remember is that no action or no new feature you add to the database system should ever have to require the system to restart in order to take effect. The commercial guys are slightly better than the open source guys. The open source guys are getting better at this from release to release, but no system is perfect, right? And the reason why this matters a lot, other than there's obvious downtime involved, is now because you have to model how long that downtime is going to be. So there's a knob in MySQL where you can set the log file size. And depending on what the current value is and what you change it to, that'll affect the downtime you have after a restart. So if my log file size is 5 gigabytes and I set it to 10 gigabytes, I can start right away because I don't have to resize anything. But if it's 5 gigabytes and I go to 1 gigabyte, then it's going to take a long time to compact the file to get back down to 1 gigabyte. So now you have to model all of this, and this makes the time it takes to apply changes slower and slower. So this is the reason why we had to build our own system from scratch, is because Postgres can't do this. All right, I'm short on time, so I'm going to skip ahead a couple of these. But one obvious thing is that you want to be able to have a notification anytime an action changes, or when it starts and when it completes. And again, you need this to know in your models about, am I getting slower because I'm building an index, or am I getting slower because the index I just built was a bad idea? So this gets hard when you have things like, I want to scale out for my workload increase 1 day from now, so I'm going to scale out, and that's going to make me slower. But that's actually the right thing because I'm going to need to be able to meet that SLA in the future. So how we actually handle that, we don't have a good idea yet. All right, I'm going to skip ahead to the last one because I want to finish off with talking about Oracle. If it'll let me do that now. OK. It's hung. I broke it. OK. OK. Sorry. OK. The last one that I think is really important is that you want to be able, if a lot of data systems are running in replicated environments for high availability, and you actually want to be able to leverage the fact that you have redundant resources to collect more training data to improve your algorithms. All right, so in order to do this, though, you need to have your replicas be able to diverge from each other and have different configurations. So let's say you're running in a simple one master, two replica setup, and you want to pick indexes. So what you'll do is on your master machine, you'll have the best index you've ever seen so far for this table. But on your replicas, you'll try out different indexes and see whether they're actually better. And so let's say this guy up here, the first replica, his index actually is better and improves performance than what the master currently has. So we want to go ahead and flip the master to have it use that one. Right? So this is sort of obvious, but things get tricky now if the replicas are choosing bad configurations and they actually can't keep up with the workload demands of the application. So let's say this bottom guy here, its index is actually a bad choice, and it's falling behind. Right? So this is bad because if the master now crashes and we have to fail over to this replica here, we don't want to have a five-minute pause while we have them replay the log and catch up where we should be, right? Because that's downtime. And that defeats the whole purpose of having a highly available setup. So what we need to be able to do is recognize early on that this configuration is a bad idea and either reverse it, kill the machine and restart it back with the correct configuration, or just undo it and try to catch up as soon as possible. So as far as I know, no database system allows you to have divergent configurations at the level that we're talking about in here, that's necessary to work in a machine learning-based environment. All right, so I'm going to finish up real quickly with a rant about Oracle, as promised. So you may have seen an announcement last year where Oracle came out and said, we have the world's first self-driving database management system, right? Larry Ellison got on stage, the CEO and founder of Oracle got on stage and says, this is the most important thing that the Oracle Corporation has done in 20 years. So I was slightly miffed about this because, not that I thought they were going to acknowledge me, but at least say something that, we had this idea way before them, but we published a paper in Cider several months before they put out their ideas. So I sent Larry an email and I said, hey, I saw your announcement, but it was kind of hurt that you didn't say anything about us. We've been working on this project for a while. How can you say that Oracle has the first world's first one, right? He didn't respond to my email. That's okay. He never responds to any of my emails. But we can break it down and see what he actually said, what's actually going on. So there's 5 key ideas that they're claiming that makes their system autonomous. So the first is automatic patching. That's sort of a nice thing, but I wouldn't call that self-driving because that's just, every time a new version comes out, you apply the change without any downtime. The middle 3 guys here, automatic indexing, recovering, and scaling. Well, these are essentially the same kind of tools that I talked about before under the self-tuning era from the 2000s, right? So these are essentially the same tools that Oracle made back, a decade ago, but now they're running them in a managed environment for you. So for the same limitations that I talked about before, they apply here, right? So these are all reactionary measures, and they're not doing any transfer learning. They're not able to learn anything from one action or one change to help improve changes in the future. So for this reason, I would claim it's not self-driving. We have an argument about the philosophy of what it means for a database system to be self-driving, right? If they're reactive enough, then you can't really tell it's not actually doing any forecasting. I can talk offline about what I think they're doing in the future, but I can't say that here because it's on video. And then the last one, they have automatic query tuning. So if you're familiar with the database literature, this is also called adaptive query processing. The basic idea is that, say I have a really complex query with a bunch of joins. I've run it through the optimizer the first time. I get a query plan. And then as I'm running it, I start to think, well, this is actually not the best plan for me. So rather than continue with the crappy plan I started off with, I just go back to the optimizer and say, hey, this is not working out. Give me a new plan. Right? And then you pick up where you left off, or you restart the query with a better plan. So this is not new to Oracle. This is not specific to Oracle. As I said, this goes back a long time. In the literature, it's called adaptive query processing. Microsoft announced in 2017 that SQL Server now ships the same feature. But IBM DB2 had sort of something very similar called the Learning Optimizer, LEO, from the early 2000s. But it's even older than that. This actually goes back to the 1970s. This is the way basically Ingress's query optimizer worked, right? They were actually doing this. They were rerunning the optimizer on a per tuple basis because they really couldn't do any joins back then, and they were worried about tables with maybe 100 tuples, right? So for them, this idea was fine. So again, this idea is not new, and I think what's going on for the self-driving system as it exists today, I wouldn't claim that's self-driving. All right, so to finish up. I think that autonomous data systems are achievable in the next decade or so. It's a lot of research, a lot of unsolved problems to work on, but I'm pretty excited about where we're going with this. And for anybody that's actually working on systems, you should always be thinking in the back of your mind every time you add a new feature that how that feature is going to be able to be controlled by a machine. Don't assume there's going to be a human that knows what the hell they're doing and knows how to set the knob for every single application, right? You should always think about, am I exposing the right information? Am I going to have to restart my system? What's going to happen if this thing's controlled by software, right? Oh, sorry.
Энди, ваша база данных теперь оптимизирована и готова к использованию.
Okay, awesome, thank you. So the demo's done. Let's go check on it again, right? Sorry, I forgot about that. All right, so let's refresh the page. Right, and there we go. So after 5 iterations, our best result was 2,600. So we went from 600 transactions a second, and we were able to get up to 2,600, right? And there's a little dip now because after that, because it's doing exploration to say, well, there's other parts of the solution space for your knobs that I don't really know about. I think it might help, but let me try them out. It's actually quite conservative, so you're not getting a huge drop in performance. And then it says, oh, well, actually, that was a bad idea. And then it tries to reverse it and tries something else, right? So the main takeaway here is you actually probably would not want to run this in production because the algorithm is going to be, exploring the solution space and try on different configurations, and you may not be able to meet your SLA. But you could tune the service to say, well, only try things where I think I'm going to get better performance, and that'll ensure that you're always sort of going up. Okay. All right. With that, we're done. I'm happy to answer any questions that you may have. Thank you.
Hi. I have two questions.
Go for it.
First of all, your solution space is very big, so you are optimizing disk I/O, memory management, possibly adding or removing indexes. By once you get a large space, it's harder to find a maximum, and so you could find a local maximum. And so why would the entire approach seems to be questionable compared to optimizing inside the database? So imagine the I/O subsystem optimizing itself and indexing subsystem optimizing itself based on not from the outside. So actually it turned out to be a single question that both of them are.
All right, so to repeat your question is, and to be specific, are you talking about the Autotune tuning service or the Peloton system?
The tunings, well, part of the Peloton is that you're self-driving.
Yes.
So you're tuning yourself, but your model is the same in both cases. So
no, it's not the same. So his question is, in the case of Peloton, are we assuming that we have one giant model that we can use to predict performance for the entire system, or is it individual subcomponents that we're using? So we haven't completed that part yet, but the plan is to do individual components, right? And his point is actually correct. If you try to model the entire solution space or the runtime behavior of the database system, disk I/O, networking, memory usage, everything, then the dimensionality is massive, and there's no way you're going to be able to converge to a good answer. Absolutely, and I think the right way to do it is to carve off little pieces one by one. Thanks. But then those, to be clear, those are models that you use to predict the runtime behavior of the system, right? It's the reward function of applying a change. And then you need to then have weights and say, all right, if I apply this change, it affects my memory model this way, and that I think that has the most effect, and I'll weight that more than disk I/O. Right? So there's a bunch of layers we're doing above this. Right? And the self-driving cars essentially work the same way. They have separate things for the wheels, separate thing for what's on the side of it. Right? Nobody builds a single model.
I actually have many questions, but not to spoil anyone else.
Okay.
I'll try to make very short. So one thing is that you mentioned that for Peloton specifically, you want rapidly changing things.
Yes.
Actually, you know very well that in Postgres, many parameters you can change runtime,
yes.
and you can, in this case, of course, will take some time. But I'm thinking of workmem, which is a very interesting parameter.
Wait, which one?
Workmem.
Yeah.
Which affects significantly your performance if you're running out of memory for the query. You can actually very easily measure the impact because you're seeing like generating temporary files, for example, and it is also very heavily contented because the aggregate of memory is limited factor, right? So one quick question is, this is one option to tune and to study tuning system, but because actually at the end of the day, what users are mostly looking at is the query performance, right?
So your question was what workmem? Sorry, what was the question?
So the question about is workmem is that this is one example of a probably rapidly changing parameter that you can use, which at the same time it affects very significantly the user experience because it's query performance directly related to query performance.
Yes.
So basically the question is, or maybe it's just more of a comment, that you can also iterate quickly on existing databases for parameters that you can change runtime. And one example is this one.
So for knobs, yes. For physical design, it's more complicated.
Yeah, sure.
And I'll say workmem 2 is actually a tricky one as well because there's things like shared buffer pool size, and that's the total amount of memory that the instance is using, but workmem is on a per worker basis.
Yep.
Right? So now it doesn't always use that amount. So that's one of the ones we had trouble modeling, and that's why we decided to, again, go with our own system. Yeah, we have it sort of uniform memory.
Yeah, it's absolutely very tricky.
Yeah.
Another thought or question is about shorter versus longer term measures. So for example, if I imagine an automatic system could try to tune auto vacuum off and checkpoint time out very, very long time. So basically that checkpoint or auto vacuum do not happen during the testing process, which provides short-term advantage, but of course not long-term. And then there's a conflicting tuning optimization, right?
So we don't do this yet, but let's use the vacuum as an example. It's very common that people turn off the vacuum during the day and be more aggressive with it at night, right? That's a human knows that. We think because we can have this aspect of temporality in the runtime behavior of the system, that we can learn that, okay, we could turn the vacuum off for this period here during the day and then just be more aggressive at night. Those are the kind of things that humans do now that we want to target.
Yeah, so actually, because of this, what I'm saying is that by measuring by 5 minutes, for example, benchmark, then the system may try to tune auto vacuum off, whereas long-term, that's not going to be good for you.
To repeat his question, he basically said, in my example, I'm doing 5-minute observation periods for my demo of Autotune. In real scenarios, you want to be much longer. Absolutely agree, yes. Because whether take the vacuum or checkpoint during the time, you don't know.
Yeah, and very, very quickly, last comment.
Oh, we should pass along in the back, sorry.
Agreed.
Thank you. I'm sorry, but a lack of time.
One more question, come on.
Okay.
I flew to Russia for this, come on.
One more, please.
Yeah, I had a follow-up question to the first one about tuning individual subsystems. So like, if you tune individual subsystems, then there are certainly settings that affect many of them. And like, I don't know, if you tune this subsystem individually, you want to have as large buffers in memory as you want.
Repeat that, sorry, tune what, sorry?
Huh?
You said tune what? I didn't hear it. I couldn't understand what you said.
I say, it was a follow-up question to tuning individual subsystems against tuning everything as a whole.
I got that. Then what's the second part you said? I missed
it. So for example, if you tune disk just I/O subsystem, you want to have as large buffers in memory as you want to reduce I/O. If you tune memory separately, you want to have as large in-memory buffers for like sorting and whatever stuff you do in memory.
Yes.
And so the buffer size, both subsystems will tune it each way. And you need to tune both together to find the optimal buffer size.
Absolutely. So just to be clear, to follow what I said to him, I agree with you. So you're describing that you have to consider the dependencies between these subsystems in your decision-making process. What I said to him was the models you build to essentially, it's like the curve of how you think, the reaction curve of how I apply these changes, how it will affect my metrics or my runtime performance. Those things you model separately. But then you build layers on top of them to say, all right, now if I'm going to change this knob, how that would affect in these individual models. And then on a per application basis, you would say, all right, well, this thing is doing a lot of inserts, so therefore that should be I/O heavy, and I should account for that to have a stronger weight than networking or something like that. Is that clear?
And insert heavy, do you detect this automatically?
Say it again?
And you said insert heavy, so you need to have to optimize for I/O. Do you detect this automatically?
Yeah, so we do, when I showed the Peloton system, I said we collect the workload traces, then we build forecast models from them, right? And the forecast models will say like, all right, I think 1 day from now, I'm gonna do 100,000 inserts a second. And then, because I know what it costs to do an insert, because I've seen inserts in the past, I know how my database is growing in size, I know what indexes I have, I can now account for that in my decision-making processes. All right, guys, they're kicking me out.
Thank you.
All right, thank you.